So next topic, we have already in the last class we have already revised the concept of the difference between finite and infinite set, which we will need in various discussion. Concept of countable uncountable set, what we mean by at most countable, from the book of Walter Rudin. Now one more concept before coming to the concept of bounded unbounded sets, supremum infimum, we need to recall, that is the concept of set theoretic inverse. So let us quickly recall the concept of countable uncountable set, finite infinite set. So using the function concept, already we have seen in the previous class, that in the previous lecture, that for any positive integer n, let Jn be the set whose elements are the integers, here Gn stands for 1 to n, and J basically denote the set of natural number, consist of all positive integers. Then any set is said to be finite if A is similar to Jn, that is there exists at least one bijective map between A and Jn for some n. Empty set is assumed to be finite. So within finite set we have A, either it is phi empty set or those sets which are similar to Jn, those sets are finite. For infinite set, which is not finite means which is not equal to empty set and which is not similar to Jn, So all the remaining sets are infinite set. Now within infinite set, it may be countable, it may be uncountable. So what are countable sets? Countable sets are those sets which is similar to set of natural number, means there exists at least one bijective map between A and set of natural number. So those sets are countable. Uncountable set, which is neither finite nor countable. Neither finite nor countable means A is not equal to empty set, neither A is similar to Jn, and neither A is similar to the set of natural number, So all those set, for example, set of real numbers, any non-trivial interval means here other than singleton set and empty set. So any interval, non-trivial interval, whether it is open closed or semi-open semi closed, or all those are examples of uncountable set. Set of irrational, all these are later I will come to this topic after covering the concept of representation of real numbers. Now so set of natural, here within countable, set of natural number is itself countable set of integers, we will see that all these sets are countable. At most countable, if either it is finite or countable, at most countable means either it is finite or countable, means either A is equal to phi or A is equal to or A is similar to Jn or A is similar to set of natural number. So all those sets comes under at most countable as per the book of Walter Rudin. So this is standard definition we will use, already I have discussed this one. Now there are properties. Countable sets are sometimes called enumerable or denumerable. For two finite sets A and B, we evidently have A is similar to B or A is equivalent to B. This is the notation for equivalent, that is there should be 1:1 correspondence between those two sets, which we are calling equivalent. So we evidently have A is equivalent to B or A is similar to B if and only if A and B contains the same number of elements. But here there is very important remark, that for infinite sets, however, the idea of having the same number of elements become quite vague, whereas the idea of 1:1 correspondence retains its clarity. So if any set is finite, see there are properties that a finite set can never be equivalent to any of its proper subset. For example, let me take this one 1, 2, 4, and let me take its subset, say 1 and 2. So, for making a function, first every element of domain has to be mapped, every element of domain has to be mapped. Let me map this one. So, this is 1 1, but not onto, because 4 has no preimage. So, and if I choose this one, say, okay, so we will find that we cannot develop a bijective map between any finite set. This is finite. Why? Because this is similar to J3. I can call J3 as 1, 2, 4. So, we can develop a 1 1 correspondence between the elements. So, this set A is similar to, since J3. So, this set is finite, but it can never be similar to any of its proper subset, because we will not get a bijective map. So, this is another property of this finite set. Whereas, for infinite set, a set may be similar to, a set will be similar to at least one of its proper subset. So, this is the notation. J is referred here for set of natural number, and A is basically here the set of integers. And in the last class, I have already established a map from n to z, which is bijective. F from n to z, which is bijective, by taking map f of n equal to -1 to the power n into box of n by 2. And with this, since we have at least one map which is 1 1 as well as onto. So, this as per definition of countable set, z is countable, and also this set, both set are similar, that is n and z are equivalent, though n is properly contained into z. So, within infinite set, it can happen that a subset may be a proper subset of the set, but still both have same cardinality, both are equivalent. However, this is not possible for finite set. So, another example I have also discussed about this one, closed interval 0 1, say open interval 0 1, which is subset of R. The open interval 0 1 being proper subset of R, but still we can see that one can develop, there exists at least one bijective map, which I have shown by geometry, and both sets are similar. 0 1 is similar to set of real number. So, that this map f of n is equal to -1 to the power n into greatest integer n by 2, or it can be defined in this way. So, we have already established a 1 1 correspondence between set of natural number and set of integers. So, this is very interesting that natural number being proper subset of set of integers, still one can establish a 1 1 correspondence, a bijective map between n and z. And in number system, one can study that both have same allotted same transfinite number. In finite set, we use the terminology cardinality of the set, and that is equal to set of this one alif naught. This is the this notation we are using for cardinality. However, this notation is only limited to a finite set. So, its extension. So, and we will see that a set of natural number is infinite, smallest infinite set having cardinality alif naught. So, a finite set cannot be equivalent to one of its proper subsets. A finite set cannot be equivalent to one of its proper subset, that is however possible for infinite sets. Is shown by example 2.5. So, this one is a very good example in which n being a proper subset of z, but both are equivalent. So, that is what written here, which j is a proper subset of A. So, in fact, we could replace definition 2.4b for infinite set in terms of similarity between equivalent condition between a set and its proper subset, So, which is written here, that is A is infinite if A is equivalent to one of its proper subset. So, this is also another definition, another way to show to check the definition of infinite set, whether a set is infinite or not. So, one of the reason that why whenever a countable collection is given, so we can enlist, we can list it with the set of with the notation of the counting set, that is set of natural number for a countable set, because as per definition, so one can use this definition for the sequence. See, sequence is a map from set of natural number to real. If I am talking about sequence of real numbers, then so look at the definition of sequence. So sequence is any mapping, whose domain is natural number. If we are talking about real sequence of real numbers, then codomain has to be real number. Similarly, where we can extend to sequence of complex number by taking codomain C, set of complex number, instead of R, or in topology one can replace it with other topological space. So by a sequence we mean a function f defined on the set J of all positive integers by f of n, f acting on this n is coming from set of natural number, and suppose its values are given by xn, it is for n belonging to J here referred for the set of natural number. So because this set is countable, so one can use this notation because its domain is set of natural number. So one can rename it with the indices x1, x2, x3, but this renaming only we can do for the countable set. For uncountable set we cannot do this. The values of f, that is the elements xn, are called the terms of the sequence. If A is a set and if xn belongs to A for all n, then xn is said to be a sequence in A. For example, if we are taking here xn from real numbers, then we will call it as a sequence of real numbers or a sequence of elements of A. Note that the term x1, x2, x3 of a sequence need not be distinct. Since every countable set is the range of a 1-1 function as per definition of countable, if any set A is countable, then there should exist at least one map from J to A, at least one bijective map between set of natural number to the set which we are claiming to be countable. So this is the reason why every sequence, every countable set is the range of 1-1 function, defined on the set of natural number. We may regard every countable set as the range of sequence of distinct terms. Speaking more loosely, we may say that the elements of any countable set can be arranged in a sequence. Why it is arranged in a sequence? Because every countable set is the range of 1-1 function. Sometime it is convenient to replace J in this definition by the set of all non-negative integers to start with 0 rather than 1, because again that set will be countable. Union of countable, using the concept union of countable set is countable. So there are some theorems which right now I am skipping, will come back to it again. Look at the statement of these theorems. Every infinite subset of a countable set A is countable. This portion already is already covered in your lecture of this number theory. This portion is moved to in your course of number theory. Now next topic is the concept of basically set theoretic inverse, which we will use at several places. Set theoretic inverse or preimage. So this one is the definition here. Suppose f is a mapping from D to C. D and C are some sets. F is a mapping function and S is subset of C. So f is a mapping from D to C, and here S we are taking a subset of C. Then the preimage of this subset is defined as collection of all x from the domain, say D, such that its image lies inside the set S for which we are interested in taking the set theoretic inverse or preimage. image. Preimage. So, and look at here, this notation never requires in this definition anywhere that for existence of this set theoretic inverse we need 1 1 onto, that is not required. Whether the function is invertible or not, we can talk of set theoretic inverse of any set. So, within this definition oneness ontoness is not required, 1 1 and onto, injective and surjective, this is just a notation for preimage, which will be so. Let us try to understand this with the help of some example. That what we mean by the set theoretic inverse, because we will use it in the upcoming results. So, I have taken this example from the book of Essential Topology by Martin D. Crossley. Martin D. Crossley, a very good example. Look at this function f from R to R given by fx equal to 4x square minus 4x. So, if we take 4 common here, 4x common here, it will be x minus 1. So, you can see that this is the standard equation, this one is a parabola passing through 0 and 1, it has factors as 0 and 1, and x coefficient of x square is positive. So, mouth will be open upward. Now, clearly this function, this one is a function, but not 1 1 neither onto. Why? Look, function f is defined from R to R. Now, if we take any line parallel to x axis, then you can see that x1, and let me call these at x2, x1 x2 are different, x1 is not equal to x2, but their images, the image of x2 is this one, and the image of x1 is again, take its projection on y axis, this one, but f of x1 is equal to f of x2, hence this map is not 1 1, not 1 1, because for 1 1 injective, whenever the elements of domain, one can see this R on x axis and this codomain on y axis. So, this is the how we look at graph of any function. So, this map is not 1 1. Now, also this map is not onto. Why this is not onto? Why this map is not onto? Because this map is not onto because our codomain is the set of real numbers, and within real numbers we have 0 positive real numbers as well as negative real numbers, and this codomain, for this we need to look at the y axis. So, we need to check whether if it is onto, then every positive real number as well as 0 and negative real numbers, everyone has all these real numbers should have preimage. Now, the negative real numbers which is below this point, actually the midpoint of 0 1 is half. So, this value on y will be f at half, f at half. So, f at a half will be 4 into half whole square minus 4 into half, that is 4 into 1 by 4 minus 2. So, 1 minus 2, that is minus 1, minus 1. So, this one is minus 1. Now, if I choose any real number less than minus 1, then you can see that there is no preimage, it is not cutting anywhere on this function. If you draw a line below minus 1, it is not going to cut any function. So, see the image, suppose we are interested to find the preimage of 24, then I need to draw a line passing through 24, it is going to cut here, and corresponding to this we have 3 as well as minus 2. So, 3 and minus 2 are preimage of 24. Now, can I do for those negative real number which is less than minus 1? I cannot do. This is not going, this line is not going to cut the graph of 4x square minus 4x anywhere. So, this is the reason why negative real numbers less than 1, real numbers less than minus 1 have no preimage, have no pre-image. Hence, if there is at least one map, one point from codomain which is having no pre-image, then this map is not onto. This map is not onto. So, this one is an example of a map which is neither 1 nor onto. But still we can talk of the set-theoretic inverse. So, you can see that here it is already solved that the set-theoretic inverse of R is whole R. Why? Because as per definition, the set-theoretic inverse, the set-theoretic inverse, look here, recall what we mean by set-theoretic inverse. If F is a map from, say, let us take the same notation here. If F is a map from, say, D to C, if F is a map from D to C and suppose S is subset of C, then the set-theoretic inverse of the set S is defined as collection of all x belonging to D such that f of x belongs to this S. So, we need to follow this definition, and within this definition nowhere 1 is onto 1 and onto is required. One can talk of set-theoretic inverse for any function. So, let us check why f inverse of R is whole R. So, we need to look at, in place of S we have set of real numbers. So, by definition we need to look at all those x, we need to look at all those members from the domain. Mapping is from R to R, mapping is from R to R in this case of the given function. So, I need to collect all those x such that the image of this element x is within this set R. So, what are those elements which is mapping to R? Look here, this image, I need to look at R, what are those elements x here from the domain R whose image is within the set S. So, those elements which are mapping on this R, we have both. Corresponding to this we have positive as well as negative members. In general, also 0 is also there, 0, this at 0 we are getting 0. So, this means all negative real numbers as well as all positive real numbers. For example, this, if I draw a line parallel to the y axis, parallel to the x axis, then corresponding to this we have those x whose image is within this R, whose image is within this R. So, this is the reason why, and this one has also image within this R. Hence, negative real number as well as 0 as well as positive real number, all these are have images in R, within R. Hence, f inverse of R is R. Why f inverse of empty set is empty? F inverse of empty set. So, I need to look at that what are those x from the domain whose image is within this empty set. So, since set is empty, so there is no image which will belongs to this set, hence f inverse of phi has to be phi. Now, let us try to understand it with the help of another example. F inverse of -1 to infinity is equal to R. Why? -1 to infinity. I need to look at all those images, all those points from the domain whose image is within -1 to infinity. So, -1 again, -1. Yes. Now, look at this one. I need to look at all those elements from the domain whose image is within -1 to infinity, -1 to infinity. This is the set. So, on y axis -1 to infinity means from -1 to infinity, this whole axis. Now, draw any line parallel to this one. So, we are getting the positive real number as well as negative real numbers including 0. So, whole R is there, collection of all those x is basically whole R, set of real numbers. So, this is the reason why set-theoretic inverse of -1 to infinity is equal to R. Let us do some more question here. Yes, f inverse of 0, set-theoretic inverse of 0. So, f let me solve this one. F inverse of 0 is 0 1. Why there are only 2 points? F inverse of 0. Just apply the definition. As per the definition, this one is your set. So, as per definition, set-theoretic inverse of any subset of codomain is defined as collection of all x from domain such that image is within this set S. So, in place of S we have singleton 0. So, I can write this as F inverse of singleton 0. This is collection of all those x from domain. Domain is here basically set of real numbers such that image is within singleton 0. Image is, just compare it first of all with the definition of the set theoretic inverse. Now, what are those elements from the domain whose image is within singleton 0? So, image always look on y axis, this 0, at 0 we are getting 0 and at 1 again function is taking value 0. So, there are only 2 points 0 and 1 whose image is lies within the singleton 0. So, this is the reason why we have the point 0 as well as 1. So, F set theoretic inverse of 0 is 0 1. Similarly, one can check other results. For example, F inverse of minus infinity to minus 1. This is empty set. Why this is empty set? F inverse of minus infinity to minus 1. I need to look at all those members from the domain whose image is within minus infinity to minus 1. Now, if look at from graph, minus 1 is here on y axis. So, minus infinity to minus 1, I need to take this portion. Is there any element from the domain which is mapping to this one? If I draw any line parallel to x axis below minus 1, then it is not going to cut anywhere the graph. So, I will not get any points from the domain which is mapping to this one. This is the reason why F inverse of minus infinity to minus 1 is empty set. So, this example I have given just to ensure that for existence of set theoretic inverse, we do not require function to be 1. If it is invertible, then it is okay, otherwise not invertible, then again we can talk of set theoretic inverse. So, this is what mentioned here. We see from this example that the pre-image of a set can be a single point or a set of points, or it may be empty set. For example, in this we have shown it may be empty set, it may be empty set, it may be singleton, or it may contain some finite set, it may be an interval. Look here, here we have the interval. The notation F inverse S can be confusing because it looks like we are assuming that F has an inverse function F inverse. This is not the case. We can define pre-image of for any function invertible or not. Pre-images behave very nicely. Very nicely here stand for that we will get equality with respect to other mathematical operation as the following results show. For example, if F is a mapping from S to T and UV are subsets of T, then set theoretic inverse of U intersection V is equal to F inverse of U intersection F inverse. In set theoretic inverse, we will get directly equality sign, whereas in case of direct image, that is range set, we may have containment relation. So, similarly, set theoretic inverse when operates on union, we will again get equality sign. Set theoretic inverse of phi is always phi, and set theoretic inverse of whole codomain is always the whole set S, the domain. Why? Because the images, we need to look at all those images which is mapped within T. F inverse of T means I need to look at all those x from the set whose image f of x belongs to T. Since f is a function, so every element is going to be within contained into T because T is its codomain. Hence, this is the reason why the whole S is its value, the whole set domain. So, under set theoretic inverse, F inverse of empty set is always empty, and F inverse of T is always the F inverse of codomain is always the domain. But this is not true in case of direct images. So, let us do some of the example. I am giving some hint how to prove the first one. we need to show that in set theory, to show A equal to B, I need to prove that A is contained into B as well as B is contained into A. So, we will start from this one. Let us take an arbitrary element x in F inverse U intersection B and just use the definition of set theoretic inverse. Then see, F inverse of set is equal to collection of, if F is a mapping from say S to T, F is a mapping from S to T, then how to define set theoretic inverse of, say, let us take another notation, because here F is itself a function from S to T. So, let us take U as a subset of T. So, F inverse of U, set theoretic inverse of U is collection of all x belonging to the domain such that image lies within the set U. So, x is a member of, I can write it as, let me write it F inverse of U. Yes. So, F inverse of U is collection of all those x from the domain S such that Fx belongs to U. So, since x is member of F inverse U, so I can rewrite is that whenever x belongs to F inverse of U, this implies f of x belongs to U. So, just use this definition again and again, you will get an idea of this proof. I need to use this notation that whenever x belongs to F inverse U, this implies Fx belongs to U. So, x belongs to F inverse U, here x belongs to F inverse U intersection V, this means Fx belongs to U intersection V. Here we have intersection operation U intersection V, so I can rewrite this means Fx belongs to U as well as Fx belongs to V, use the concept of intersection of from set theory. Hence, again Fx belongs to U, look, Fx belongs to U means x belongs to F inverse of U. So, again use this notation. So, I can write from here x belongs to F inverse U and x belongs to F inverse V. This implies Fx belongs both of F inverse U as well as F inverse V. So, we have proved the first part, containment from left hand side. Conversely, one can do it for the similar one can use for the second one, containment from right hand side. Use similar argument. So, one can take it as assignment. Now, this reason already I have explained that F inverse of phi is always empty. Why? F inverse of empty set is always empty. In this case, we have taken map F from S to T. Okay, we have taken this notation F from S to T, and we are taking phi here. Phi empty set is subset of every set. So, now F inverse, as per definition, F inverse of phi will be collection of all those x from the domain here in this case is S, such that its image Fx belongs to the empty set, Fx belongs to the empty set. Now, empty set is empty, so it is not going to contain any of the elements. So, there is no x such that Fx belongs to empty set, hence this collection is empty, this collection. So, this is the reason that under set theoretic inverse of empty set has to be empty, or preimage of empty set is always empty. So, these are some of the results which I will use in upcoming proofs. We need to have the basic idea of set theoretic inverse. Next topic I will cover about some idea of interval order relation that we will use, and after that I will come to the concept of bounded and unbounded set and so on.